Good morning, everyone. This morning's speaker is Alex Robel. Alex has a PhD in Earth and Planetary Sciences from Harvard University. He spent some time at the California Institute of Technology and the University of Chicago before becoming an assistant professor and leader of the Ice and Climate Group at Georgia Tech. Alex's work is generally interested in climate and cryosphere, including lab experiments, numerical modeling, and observations. And in particular, he's interested in dynamical systems theory, ice sheet instabilities, and sea level change. With that said, it'd be great if you could just take over from here.
Great. Thanks, Greg, and thanks for inviting me to talk to y'all today about some of the work that I've done with collaborators over the last few years to really answer this question of why are projections of the Antarctic contribution to sea level rise so uncertain. So what I'm going to talk about today is a theory based on a relatively simple model for marine ice sheet dynamics, which predicts what the spread in projections of Antarctic ice sheet melt under future warming, what that should be. And I'll talk a little bit about some of the challenges that result from sort of the implications of that theory, and then what work we're doing now to kind of push the problem of uncertainty quantification and attribution studies of Antarctic ice sheet change forward into the future. And so all this work that I'll be talking about today is primarily in collaboration with Helen Sorosi at JPL and Gerard Rowe at the University of Washington. Okay, so first I'll just give a bit of an introduction to sort of what the problem is that we're trying to solve exactly. So here you see a map of the bedrock topography of Antarctica. So if we took all of the ice off the Antarctic ice sheet, the brown bits here, brown and green bits here, would be the areas that are above sea level, and the blue bits would be areas that are below sea level. So Antarctica is actually really an archipelago of islands that is really only connected into sort of a single continent by the presence of the modern day ice sheet. And we know fairly well now, over work done over 50 years in the glaciology community, that the retreat of marine ice sheets like this, and so when I say a marine ice sheet, I mean an ice sheet like Antarctica, and particularly West Antarctica, that is the part here that's on the left-hand side of the image. Marine ice sheets are those that are primarily situated below sea level. So you can see, it's primarily blue here, which means Antarctica is a marine ice sheet. And we know from about 50 years worth of theory and modeling and observations that, largely speaking, marine ice sheet retreat is controlled by this kind of bed topography, right? So the classical prediction, and I'll get more into that here in a few slides, is that on places where the bed topography becomes deeper towards the interior of the ice sheet, that is to say, where the ice sheet is flowing uphill at the edge of the ice sheet has the possibility to be unstable. And so here have been just a selection of two, actually not so recent now, these are back from 2014, but there have been a number of studies that have made similar predictions saying that the retreat of two glaciers in particular, Thwaites and Pine Island, and I'll come back to talk about Thwaites Glacier later in the talk, is largely controlled by the bed topography through this process called the marine ice sheet instability. And I'll get back to that again in a few slides. So, okay, so retreat is controlled by bed topography. The problem is that even though that is the case, and we know bed topography, we're certainly learning more about bed topography, but we know bed topography fairly well. In projections, in ensemble or parameter perturbed ensemble projections of Antarctic ice sheet retreat over the next several centuries to several millennia. So on the right-hand side here are just two examples of the Antarctic contribution to sea level rise, where the y-axis, the bottom one has a cutoff y-axis, but they're both meters of sea level rise contribution from Antarctic ice sheet melt overcoming centuries and millennia using two completely different ice sheet models. And what you can see here is that there is considerable spread in these projections, even though in both cases, so in both of these cases, what they're doing is they're perturbing some physical parameters in the model due to uncertainty in the processes. We don't really know what the parameters should be in reality, but they're using exactly the same bed topography. So if bed topography plays such a strong role in dictating ice sheet retreat, why do we have such large amounts of uncertainty, right? So to put this in context, we're talking here about order, several meters worth of uncertainty in sea level rise on timescales of a few hundred years. And to put that into context, for about every meter of sea level rise uncertainty, we're talking about an uncertainty of inundation for approximately 100 million people, right? So a large fraction of the world's population is actually and where they live is actually encompassed within this sea level uncertainty. So this is a problem of significant consequence. And what I'm going to talk about today is basically why. Why is there so much uncertainty in these types of projections? The other issue that I'm going to talk about a bit more is sort of this issue of the limits of predictability, which is a problem that is well known in the climate modeling community, the problem of so-called irreducible uncertainty. So the idea here is that the climate system is sort of an intrinsically variable and noisy system that has all kinds of internal variability due to a couple of modes of climate variability, internal, ocean turbulence, these sorts of things. And so in terms of, even though the ice sheets are not turbulent, chaotic fluids, to the extent that we understand how ice sheet flow works, the forcing that that ice sheets feel from climate is very much a noisy and uncertain field. So here on the right are just two examples of this, two kind of disparate examples. One is from the Greenland ice sheet, where I'm showing ice cores from Luke Trussel's Nature paper from a few years ago, which are basically a quantification of the surface melt over a large portion of the western Greenland ice sheet over the last several centuries. And what you can see is that, obviously there's been an increase over the last few decades, but that increase is of approximately the same order of magnitude as the kind of decadal variability, interannual to decadal variability that we've seen in surface melt over Greenland over the last several hundred years, and presumably back through the Holocene as well. And then on the bottom is an ocean temperature index from Thwaites Glacier from another paper in Nature Geoscience by Adrian Jenkins and colleagues, which shows sort of a more recent record of inferred record of ocean temperatures at this Thwaites Glacier, which I mentioned on a previous slide. And what you can see is that there is significant decadal variability that is approximately also of the same order of magnitude as the ocean warming that we've seen there in the last 20 years, which has driven much of the retreat that we see and much of the mass loss that we've seen in West Antarctica. So we have this noisy climate, and we want to understand how much of an influence that has on projections. So here comes to our setup, right? So the theory for this. And so you're all going to have to bear with me. There will be equations in this section of the talk. And if you have any detailed questions about it, maybe you can put it in the chat, or you can always just jump in and interrupt me. I will go through some of the math a bit quickly for the purpose of this talk, so I can also get to the good modeling bits at the end. But the idea here is I'm going to put forward a very simple model for marine ice sheet dynamics, and then I'm going to analyze it in a way that allows us to understand how the spread in where the spread in projections comes from. Okay, so we start from the basics. Here is a cartoon schematic of what a marine ice sheet looks like. So this is, if we looked in a side-on view of what the Antarctic ice sheet looks like, or the West Antarctic ice sheet in particular looks like, it looks a lot like this, right? So the sort of up direction here is sort of the vertical direction, and then going from left to right in this figure, where we're going along the flow of ice from the grounded glacier on the left to the floating ice shelf. That is, when the grounded glacier becomes sufficiently thin that its weight can be supported by the buoyancy of the ocean at the depth of the grounded glacier, then the ice goes afloat and we have a floating ice shelf. And so the bed topography here in the schematic is in brown, and we're going to call it some arbitrary function b, which we'll come back to before. But in practice, most of the Antarctic contribution to future sea level rise comes for the potential for an instability in this situation. So you can see that I've made a little bed bump here, which will illustrate the marine ice sheet instability, which I'll talk about here in a minute. So the grounding line is sort of this imaginary place. It's actually not an imaginary place, it is a real place in actual ice sheets. But the grounding line is this sort of dividing line between where the glacier is sitting on solid Earth and where it's floating in the ocean. And the simple model that I'm going to put forward here is basically a model for the position of the grounding line. So ice flow, again, goes from left to right, going through the grounding line. Here you have a portion of the bed that is reverse sloping, and I'll talk in a second about why that's important. And then we have accumulation of snow on the top of the ice sheet, which we call P, and a grounding line flux. This is the solid discharge of ice going from the grounded ice into the floating ice sheet. And so one reason why the grounding line is so important is because when ice moves through the grounding line and becomes part of the floating ice shelf, that is sort of exactly the point at which it starts contributing to global sea level. As soon as the ice is displacing water in the ocean, then the ocean everywhere has to be compensated for that. And so the grounding line is sort of like the dividing line between kind of that terrestrial storage of ice that's not contributing to sea level and being an important factor in determining global sea level. Okay, so in this very simple model that I'm going to put forward an actual equation for it here in a minute, we basically just think about the mass balance of this simple ice sheet. So again, snow accumulation is raining ice down onto the surface of the ice sheet. And we consider just the area between the ice divide in the center of the ice sheet and the grounding line. And so snow accumulation is the mass flux in, and then the mass flux out is the grounding line flux, which we'll call QG. And so in this graph on the bottom, I've plotted both of these fluxes and how they change as a function of the grounding line position, right? So the accumulation flux is simple. As the grounding line goes further and further out, you have a larger and larger ice sheet, and you're accumulating more and more snow. And so we're assuming that snowfall is just constant everywhere in this very simple model. So you just have this straight line, the blue line at the bottom, increasing with the grounding line position. And then the grounding line flux QG is a nonlinear function of the depth of the bed below sea level. And there's been a lot of very important work done on that problem of understanding what this beta exponent is over the last 15 years. There's been a number of papers revising that. Suffice it to say, it is an exponent somewhere between approximately 3 and 6. And this nonlinearity in the system is actually quite important for the problem of understanding stability. And I'll return to that later on. Okay, so in a very simple graphical stability analysis, we can just find the place where these two curves intersect. Those are the 3 black lines, and those are all potential steady states for the grounding line position, right? So we can consider this situation in this cartoon, which is the rightmost black dot. And that is a stable grounding line position, because if we moved the grounding line a little bit, let's say if we made the grounding line a little bit further out, so we moved it a bit to the right, then the grounding line flux out would be greater than the accumulation coming in. And so overall the mass balance would be negative and the grounding line would return to its original position. Okay, so that's a stable grounding line. Now, the question that we can consider is what happens when we decrease the amount of accumulation due to snow, or maybe we just change the balance between the average balance between accumulation and surface melting. These all have the same sort of basic, or the same basic effect, which is that as we turn down P, this blue line starts to move down, and the grounding line will retreat a little bit. As you can see here, the grounding line has retreated a little bit, But we will reach a point when we get to the sort of peak in this bed topography here, when the steady state disappears, right? And so this is a situation where the grounding line has retreated onto this part of the bed slope that is getting deeper as towards the interior of the ice sheet. And this is a situation where you have an instability, which is commonly called marine ice sheet instability. This bifurcation, which, for those of you who think about these things, this is a saddle node bifurcation in a bed topography like this. And I've thought a good deal more about like what that bifurcation looks like, but I'm not going to talk about that today. Happy to talk to anyone about who's interested in that. But the idea here is that when the grounding line gets onto the reverse sloping part of the bed, you get into a situation where when the grounding line retreats, the ice flux through the grounding line increases, so there's more flux going out, and the catchment area of the glacier also decreases, which means the mass flux going in also decreases. So both of those lead to a situation where there's a positive feedback on the ice flux through the grounding line that leads to basically irreversible retreat of the grounding line with no further change in climate, right? So again, just going through the sequence, if we decrease snow accumulation little by little, we get to a point where a small decrease in snowfall accumulation will cause the grounding line to retreat by, in this schematic, many hundreds of kilometers without any change in climate. And so this is called the marine ice sheet instability. And this is largely what governs the most of the retreat that is simulated in models of the future evolution of the Antarctic ice sheet. Okay, so if we want to write all of this down into a set of equations, the simplest model that we can write down that captures this, these grounding line dynamics and this instability looks like this. So we have the grounding line position L, we have the grounding line ice thickness Hg, which is just set by the bed topography, as you can see here. So we just have some prescribed function B, which determines the bed topography. And then we have our accumulation flux in, that's our positive term on the right-hand side, grounding line flux out, which again is just some nonlinear function of the grounding line ice thickness. And okay, and so what I've talked about there, that will sort of capture grounding line dynamics. What I've added here is an extra term which sort of represents ocean melt at the grounding line. There's no particular reason why we need to look at ocean melt. We can also think of just accumulation flux in, but for the purpose of this problem, we know that in West Antarctica, the ocean is quite variable on timescales of years to decades, as I showed in that previous slide. There are observations which indicate that there's considerable decadal variability in the ocean circulation around West Antarctica, and there's a lot of interesting reasons for that, having to do with sort of modulations in the wind curl originating from teleconnections from the tropical Pacific. There have been a lot of really interesting papers written on that in the last 5 years. But for the purpose of this study, I'm just going to consider that the ocean melt is a stochastic noise term in this simple model. So what we have here is not just a sort of a plain differential equation or a simple dynamical system model, but actually a stochastic differential equation where the sort of noise forcing in the problem is coming from the internal variability of the ocean. And everything that I'm talking about from here on out is in a paper that we had published in PNAS last year. So you can find more details on that there. Okay, so if we just take this model and we put some idealized bed topography and stochastic ocean noise into the model, and we can evolve it forward using some very simple ensemble simulations, right? This is a 1 degree of freedom model, with one prognostic variable, so it's trivially easy to, run 10,000 ensemble members on your laptop in a few minutes. Okay, so what I'm showing here are the ensemble spreads for 4 different scenarios. So the green shading indicates the envelope of the grounding line position over a few centuries for a situation in which we have a stable bed, right? So a forward sloping bed, there's no marine ice sheet instability. and the ocean forcing is simply interannual variability. So what you can see here is that the grounding line position stays relatively close to the initial condition, and the spread of the projections is quite well constrained. In the orange case, what I've now done is I've introduced a reverse sloping bed with the exact same variability, ocean variability that we had before. So now we see two things happening. One is that the marine ice sheet instability is kicking in. So even though in all of these cases, there is no trend in the forcing, right? It is initiated just over the instability in the orange case, and then it's just allowed to evolve with the noise forcing over time. And so what you can see here is two things in the orange case. One is that, of course, we have the marine ice sheet instability. So all the ensemble members are retreating by some amount, even with no trend in the forcing. But also we have more spread in the projection. So moving to this bluish, purplish case, depending on how you see these things. We have the same exact reverse sloping bed, but now we have interdecadal variability in the ocean forcing, the same magnitude of variability, just with greater persistence. So we put in an autocorrelation timescale basically into the stochastic noise forcing, and the spread of the projections is in the blue shading here. So what we can see here is that even though the mean response of the ensemble is approximately the same, the spread is considerably more. And this is just due to the fact that we've moved from interannual variability in the ocean forcing to interdecadal variability in the ocean forcing. And then finally, in the pink shading, which sort of encompasses all of these, rather than having variability in the ocean forcing, we actually keep the ocean forcing constant in time, and we select it from a Gaussian distribution of an uncertain ocean forcing. So this would represent something like process uncertainty. We don't know what the average ocean forcing should be, but it's not variable in time. It's just variable because we don't know what ocean melt should be. And so you can see here that this is sort of like the end member of the most persistent ocean forcing, and this produces the most spread in projections. Okay, so a few things that we've learned here is that basically for stable grounding lines or just for stable marine ice sheets, the ensemble spread and uncertainty, it remains bounded in time. So it looks sort of like a random walk, which we know should be approximately bounded to a square root in time. For unstable grounding lines on retrograde slopes, the ensemble spread and uncertainty grows exponentially without bounds, right? So if we kept on running this out, assuming that you never ran out of retrograde or a reverse sloping bed, the spread of your ensemble would just continue to grow exponentially in time. It also, and you can't really see this because I haven't showed you a probability distribution yet, but you can get a sense here that the spread in that ensemble, so what I'm showing here sorry, I should have said this at the beginning, the shading here is the plus or minus 2 sigma of the distribution of the ensemble. And so the other thing is that you can start to see that the ensemble is skewing more to the bottom, right? So it's skewing more towards worst case scenarios. And I'm going to show that this is actually a fundamental consequence of marine ice sheet dynamics as we currently understand them. And then finally, the ensemble spread or uncertainty grows faster for forcing that is either persistent in time or uncertain in the time average, which is sort of the end member of persistence in time. So the idea here is that as you go from sort of interannual variability to interdecadal variability to multidecadal variability in the forcing, you're going to produce more spread in your ensemble. Okay, and so the basic reason here, apologies for the silly cartoons, but just to sort of explain what's going on, we understand what's going on here exactly. This is actually a very well understood consequence of stability in stochastic dynamical systems. So in a neutral dynamical system, so that's illustrated here by this school of fishes that are just bouncing around due to random walks. So the dynamics of the system are not pulling the fish one way or the other. And so they just bounce around due to a random walk. And we understand that the spread of their paths should be bounded by the square root in time. In a stable system, there still is going to be some non-zero spread, but slowly over time, the spread of the trajectories will converge, right? So in this case, the fish are sort of going towards something, you know, that they want to all get to in the same place. That would be like the stable, steady state in our dynamical system. And so that keeps the spread of the ensemble, the trajectory ensemble, bounded in time. In an unstable system, so like in this case where the shark is chasing all the school of fish, the fish just want to get away, right? And so they're going to spread quickly in all directions. And so in an unstable system, that's exactly what we see as well. Okay, and so this is where it's going to get a little bit mathy for like 2 slides. But the nice thing that we have is that we have the entire field of statistical physics and statistical mechanics to sort of help us understand what is going on in this problem. And beyond just evolving, numerically evolving these systems, we can actually analytically determine how we expect the leading order statistical moments of the ensemble distribution to evolve in time. So we use this method called stochastic perturbation theory, and it's not too different from like a normal perturbation type analysis that you would use in an applied math context. But the only difference here is that we are expanding the system about the deterministic dynamics in powers of the amplitude of the noise forcing. And so really all this requires is that for any arbitrary stochastic differential equation, even for an arbitrarily nonlinear one, we can linearize it about the stochastic dynamics, so that's sort of what you see here, where F is the deterministic part of the model, sort of all the dynamics that we would normally have on the right-hand side of the model. And then this method allows us to linearize it, and then to expand the deviations about the deterministic dynamics in terms of the amplitude of the noise forcing. And so what that eventually allows us to do, and I'm sort of, again, happy to answer more detailed questions about all the math that comes in between these 2 boxes, is basically we can rewrite any stochastic dynamical system in terms of, or assuming it's sufficiently smooth, in terms of the Fokker-Planck equation. So this is sort of one of the main governing equations of statistical mechanics. It's been around for a long time. And the point is, it describes the evolution not of a deterministic trajectory, but it actually describes the evolution of the probability distribution in a system, the system that we've linearized. So the point here is that this is already well studied. We're not doing any developing any new mathematical techniques here. We can simply apply the known solutions to this equation in order to derive expressions for the variance of the ensemble and the skewness of the ensemble. And so that's exactly what we get to. And basically we learn 2 things here. One is that as we saw in the numerical, in the numerical examples and the numerically determined ensembles, the spread of the ensembles grow exponentially in time, and that's exactly the prediction that's made here. And the growth rate of that, the growth rate of the ensemble spread, or sort of the growth rate of uncertainty, is simply proportional to basically the stability parameter that governs the marine ice sheet instability. So if we simply take the derivative of that, our simple deterministic model with respect to the grounding line position, we get the stability parameter, which I've written as omega here. And this omega parameter is simply dependent on how reverse sloping the bed is, right? So the more steep the reverse sloping part of the bed is, the faster your grounding line will become unstable, and the faster the growth rate in the spread of or in the uncertainty of your ensemble. And similarly, we can find that the skewness should always grow in the direction of worst case scenarios, or faster retreat. And so this shows the bottom part here. And this is a function, this is a bit more of a subtle point, but the fact that the skewness will always grow in the direction of worst case scenarios is simply a function of the nonlinearity of our system, right? So that beta exponent, which governs the grounding line flux, the more nonlinear that is, the more skewed your system dynamics will be. And so for like reasonable values of beta for this nonlinearity parameter, we should assume that skewness will always increase during the instability.
Alex, can I stop you one moment?
Yeah, absolutely.
Question in the chat from Gavin. I hope you don't mind me.
Okay, I can't see the chat, so I'll just.
Any chance you would mind asking? Would you like to ask the question?
Oh, okay. I got the chat here.
No, I can read it out. Sorry, Gavin's probably wrestling his young one.
I'll just read it out. So Gavin asks, this is only going to work with small linearizable noise. No, bigger noise in some respect will violate the linearization. So determining limits to the SPT applicability is key. Yeah, absolutely. You're right, Gavin. As with any linearization, right, you are sort of hemmed in by the linearization itself and by the amplitude of the actual noise. And so what I'll show here, I'll actually just skip over this slide so we can get to the good bits faster. So here we compare the numerically determined ensembles, the statistics of the numerically determined ensembles, which are the solid lines, to the predictions made by the theory, which are the circles here. And so what you can see is, for the most part, and obviously I've done myself some favors here by only showing like the first few centuries of the simulation. Over time, as we depart away from the place where we've linearized the system dynamics, there will be greater and greater departures from this system. I think the utility of this theory, less so than its ability to like exactly predict what the uncertainty should be, because of course this is an incredibly simple model. So its ability to, let's say, describe what you might see in a 1,000,000 degree of freedom ice sheet model is, going to be limited in many ways. But what it tells us is what are the sort of physical parameters and physical processes which should really be the main things governing the growth rate of uncertainty. It could be that the actual growth rate is going to be, somewhat different or become somewhat different over time from the prediction here, but certainly like the direction and sort of the main physical controls are going to be described by the theory, and that's exactly what we see. I'm going to show here just in just a few slides time how this actually compares to like a real ensemble and a real ice sheet model with a real glacier. And so we'll kind of see how this theory pans out. So Gavin, I hope that answers your question, but I'm happy to go into more detail maybe at the end of the talk. Okay, so I just showed the theory. The theory does a pretty good job of describing the simple model itself. So the linearization holds up, on time scales of, let's say, a few hundred years, and as Gavin mentioned, under relatively small amplitudes of noise forcing, which might not hold up in real situations where we have potentially large amounts of noise in the forcing. Okay, so what we want to do here now is to test this against sort of a real glacier that is undergoing instability. So Thwaites Glacier, which is about a Florida-sized glacier in West Antarctica, which I mentioned before, is sort of seen as like the poster child for the marine ice sheet instability. It has enough ice within it to contribute, if the entire glacier melted and contributed to sea level rise, it would raise global sea levels by about 1 meter. And so we're going to use the ice sheet system model developed at JPL with our collaborators, Helen and others. We're going to use the ice sheet system model to simulate the evolution, the unstable evolution of Thwaites Glacier under ocean forcing over the next 1,000 years. And so just some simple details. We're only simulating the Thwaites Glacier catchment. It's 1 kilometer resolution everywhere. And then the climate forcing, the only forcing that we are subjecting this to is a constant in time average, so there's no trend, in ocean melt rate at depth, right? So this is a very simple parameterization of ocean melt rate, which is just linearly increasing with depth. And the melt rate at depth is set to have a constant time average. But we add in stochastic variability in the melt rate at depth through a first order autoregressive process with a prescribed persistence timescale. So what we're going to do is we're going to investigate the role of persistence, as we did in the very simple model and in the theory, the role of persistence in the ocean variability on the spread of the overall ensembles. And then the nice thing, one of the nice things about ISSM is that for various reasons, it's actually quite a fast model in series. So we can run many ensemble members to really robustly resolve like the whole structure of the probability distribution of the uncertainty. Okay, so what I'm showing here, it's going to be an animation, but before I start it, I just want to describe what I'm talking about here. So this is the top right corner is a plot of the bed topography underneath Thwaites. That's the color that you see there. And then the small yellow line is actually a subset of the 500 ensemble members of the grounding line. And so this is the catchment that is being simulated. So this basically encompasses Thwaites Glacier, and ice is flowing from the top right to the bottom left, where at that yellow line, that's the grounding line. Everything to the left of that is either floating or ocean. So what I'm going to show is how the grounding line in a subset of ensemble members evolves over time. In the top left corner is this max melt rate, which is prescribed with this stochastic, decadal stochastic noise forcing. And so I'm going to show how that evolves in time in these prescribed melt rates in that same subset of ensemble members color-coded to go with the lines that you see on the right. And then the bottom is the probability distribution of the sea level contribution from Thwaites Glacier as it melts. And you're going to see that sort of march to the right as Thwaites melts and contributes to global sea level rise. Okay. So, the first thing you can see, so Thwaites hasn't really become very unstable at this point. It's not doing much for the first few hundred years, but you can see all of these different melt rate ensemble members on the left. And the probability distribution is sort of slowly marching to the right. But as we get into the most unstable part of the retreat, what you can see is that the grounding line predictions spread out. I'll just run that again real quick. And the other thing that you'll notice if you look, you kind of have to look because it happens very quickly, because the sort of peak of the instability, even though the simulation's over 1,000 years, like most of the retreat occurs within a period of about 100 years. During that peak part of the instability, the probability distribution spreads out, and during the fastest period of retreat, this one glacier, due just to decadal ocean variability, contributes something like 10 centimeters of uncertainty in sea level rise, right? So I'm just gonna like come back to that argument that I made before, which is that, so every centimeter of global sea level rise impacts about 1 million more people worldwide. And here we have one glacier. Yes, it is the kind of like the most unstable glacier. It's, you know, obviously I'm helping myself out here in making this point by using this glacier as a case study. But the point is that just from the sort of irreducible uncertainty of internal climate variability, actually just internal ocean variability, we can get, you know, order 10 centimeters of uncertainty in sea level uncertainty on a long time scale, to be clear. But, you know, once we start to ask this question about a wider range of glaciers and a wider range of climate forcing, you know, then we really can start to add up large amounts of uncertainty to, you know, the kind of many meters that, similar to the many meters that we saw in that, in those earlier perturbed parameter ensembles. Okay, so we do this for 4 different ensembles, each with 500 members. And what I'm plotting here in the top is the fractional uncertainty, which is basically the standard deviation of the ensemble spread over the total amount of ice in Thwaites Glacier. So what you can see here is that for a period of a few hundred years in several of these ensembles, the uncertainty just due to climate forcing, just due to climate variability, so that's the yellow, blue, and orange cases here, which are variability, constant mean variability in this ocean melt rate. The uncertainty can amount to like several tens of % of the entire signal from Thwaites, right? And the skewness sort of shows that similar pattern, right? So in this case, this is skewness in ice volume, which means that negative skewness indicates skewed towards more worst case scenarios. And so you see during the onset of the marine ice sheet instability, when the uncertainty is sort of ramping up between like 500 and about 650 years in the simulation, you have significantly negative skewness. And this pink case is actually, again, this uncertainty, so time constant ocean forcing, so no variability, and this is just an uncertain mean ocean forcing, right? So this is, again, like process uncertainty, and this produces the greatest amount of uncertainty in our projections and a large amount of skewness. Of course, as we get toward the latter part of the simulation, the skewness actually goes in the opposite direction, which is to say that it is skewed towards better case scenarios, but that's only because we basically run out of ice. You didn't see that in the animation. You didn't see that in the animation on the previous slide, but basically once the grounding line reaches the edges of the domain, there's just no more ice. So your probability distribution becomes like a sharp peak again, because eventually all of the simulations just deglaciate the entire Thwaites Glacier catchment. Okay, so this goes, I mean, this is a kind of specifically made ensemble to sort of illustrate a lot of the points that, that we've figured with the theory. But this explains a lot of what's going on in a lot of the perturbed parameter ensembles that have been done. So this is this study that we did was the first case where an ensemble looking specifically at climate variability, internal climate variability, was run for Antarctica. But in previous studies, people have looked at perturbing parameters in ice sheet or in models of the Antarctic ice sheet flow and its evolution, and they get these various examples. The top right corner was one that I showed earlier on in the talk. And so basically this describes kind of what's going on in these various cases, which is that during the periods where you have the fastest contribution of Antarctica to global sea level rise, you have the fastest rate of growth of uncertainty. And that rate tends to be skewed towards worst case scenarios. Okay, so just some brief slides coming towards the end here. Just some brief slides. So I talked today about a paper that we already had published, and it really, for us, kind of showed us the path forward of what we need to be doing in order to start to quantify the uncertainty due to particularly internal climate variability in sea level projections. So I'm going to just talk briefly about two projects that we've recently had funded that sort of try to answer the question of how do we do this on a large scale, right? I showed a very nice contained example of Thwaites Glacier, 500 ensemble members. But if we want to answer the question of, well, how much uncertainty does internal climate variability introduce in projections of retreat of the entire Antarctic ice sheet, or the entire, also including the Greenland ice sheet, how do we start to do that? We start to run into computational limitations. We can't easily do a 500 ensemble member of simulations for the entire Antarctic ice sheet. So two projects that we recently had funded. One is the Antarctic Ice Sheet Large Ensemble project. For those of you in the climate modeling community, which I gather is a number of you, this is obviously, we are trying to sort of hitch ourselves to the growing large ensemble community. But this would really be the first large ensemble project specifically for looking at the role of internal climate variability in ice sheet evolution. So the idea here is that for most of the climate forcing, understanding the forcing through surface mass balance and ocean melt over the entire Antarctic ice sheet, the problem with using existing large ensemble products is that most of them have resolution of about 1 degree. A good large ensemble maybe has a ½ degree resolution. And so that resolution is going to basically just completely miss like most of the ice shelves in Antarctica, which are contained within a latitude grid box. The other thing is, of course, that we need a model that does a decent job of actually simulating the melt rates underneath ice shelves and also simulating the processes that contribute to surface mass balance. So what we propose to do here, and what we're starting to do just now, just this summer, is we are using some of the new runs from E3SM, the Department of Energy, global coupled climate model, where one of the main benefits of this model is that they can refine the horizontal resolution of the model in select places for particular applications. So one of the simulations that they are doing is they're doing a long run simulation, which is 1 degree everywhere except for the Southern Ocean, where it is down to 6 kilometers resolution. So we're about at 1/10 degree there, and you can much better resolve a lot of the ocean circulation that's going on underneath the ice shelves. So this should be a video. Okay, yeah, so here you can just see like a few years video snapshot from the E3SM ocean model. And so you can see all the kind of variability that you might find underneath the ice shelves in Antarctica. And so we're gonna take the output from a long run of this model, and we're gonna use statistical emulation approaches to basically build a statistical model of the climate forcing on the Antarctic ice sheet, and then use it to cheaply generate many statistically independent realizations of climate forcing on Antarctica. Then all we need to do is run the relatively much cheaper ice sheet model for all of Antarctica at a few kilometers resolution over the entire ice sheet. And then using this sort of much cheaper way for generating the climate forcing, we can generate a multi-hundred member ensemble of evolution of the Antarctic ice sheet, both over the last 100 years to answer attribution questions about what caused the recent increase in mass loss from Antarctica, but also to answer certain questions about uncertainty quantification going forward into the future.
Alex, can I interrupt you again? Sorry, there are a couple of comments in the chat.
Oh, yep.
So, Gavin says something like E3SM is great. It has high resolution, etc., but it has a very high climate sensitivity. Let's just comment from him, above greater than 6 degrees. Mm-hmm. There's a couple of questions by Vivian. Vivian, any chance you would like to unmute and ask your question?
Yes, can you hear me? Yeah. I was wondering about the Thwaites Glacier, the reverse slope, the way you were portraying it, with the inland retreat of the grounding line and how the uncertainties propagate over time. And that sort of assumes that the marine instability will continue practically to the edge, but in actuality, doesn't the topography eventually flatten out and then reverse back to a normal seaward facing slope somewhere along the length of the glacier? And the second question that I had was, if you were to consider the glacial rebound from the associated with the retreat of the grounding line, how would that affect your modeling of the uncertainties and the propagation of the uncertainties in time as you go forward?
Yeah, those are both great questions, Vivian. So to your first question, within the catchment itself, the bed does not become forward sloping again. Or there are isolated places where you have small peaks in the bed, and those slow down the retreat. And if we actually look at this ensemble of simulations that I showed before in more detail, you can actually see places where the ensemble will briefly shrink a little bit because there are basically peaks in the bed where the grounding line gets hung up on. But none of those can really stop, at least as long as the grounding line is still within the catchment of Thwaites, that retreat, at least for the kind of ocean melt rates that we impose in those simulations. Of course, once it gets further into the Antarctic ice sheet, there are other places where it could become forwards, or it does become forward sloping. But this is sort of like many meters of sea level rise later before that sort of thing happens. And then as to your second point about glacial rebound, that's of course an excellent point. And yes, there's been a lot of really excellent work recently done, basically showing that the rigid lithosphere underneath West Antarctica might cause a quite rapid rebound of the bed and a slowdown, perhaps a slowdown of the marine ice sheet instability, but not necessarily a cessation of the marine ice sheet instability. Although that being said, there are very large uncertainties in the upper Earth structure underneath Antarctica that really need to be figured out in order to determine exactly how much could that slow down the marine ice sheet instability. That of course is also dependent on exactly how strong the climate forcing is. I'll answer the other two questions quickly before I quickly go to my last slide. Gavin, you're 100% right about E3SM. I think the simulations that they have specifically done, or at least the validation that they have specifically done, looking at the kinds of melt rates that they see in Antarctica, fall within sort of observational uncertainty bounds. Observational uncertainty bounds in Antarctica are huge, so of course that's, you know, perhaps a weak validation. And, you know, I think my larger point about this is that, like, there are some good reasons to pick E3SM, particularly with respect to the kinds of methods that we want, or the kinds of questions that we want to answer. But part of the purpose of this is to provide a roadmap for ice sheet modelers for how to do this sort of thing, how to do this sort of large ensemble project in the context of ice sheet models. But, you know, the goal hopefully would be that, you know, other people would follow our lead in the future and do this with, you know, other coupled climate ice sheet modeling systems. And then Allegra asks about the surface boundary condition in E3SM. So it's a full SMB SEB model. And then a comment about the fact that there's a paper by Zelenka about Southern Ocean clouds leading to this large equilibrium climate sensitivity. So perhaps that could explain it. But I won't defend E3SM in too much detail here. I'll leave that to my collaborators at Los Alamos to do. You know, I think what I'll reiterate here again is that, you know, we're kind of running 10 or 15 years behind in the ice sheet modeling community in terms of thinking about these sorts of large ensemble approaches. And so the idea with this initial study, you know, which is, you know, a small initial study that is really just being run at Georgia Tech with some, you know, model output being provided by the folks at Los Alamos, is to show what can be done when climate model output is sort of used in this sort of emulator type way to produce large ensembles. But I'm happy to discuss more about, you know, folks who have more experience with these large ensembling type approaches, about, you know, some of the pitfalls or some of the questions about that. Okay, so I'll just quickly move on to the last slide here, which is the other project that we recently had funded, which is it's called the Stochastic Ice Sheet project. And the basic idea here is that in the hierarchy of sea level models, we kind of have at one end member of the spectrum, we have empirical sea level projections a la Stefan Rahmstorff's semi-empirical sea level projections, which are really useful. So this is sort of like you draw a regression line looking at sea level over the paleo record and sea level with respect to global temperatures. And then you use that very cheap, you know, trivially cheap model empirical model to derive many scenarios of future sea level rise. The problem, of course, is that, you know, we're sort of hemmed into the out of sample prediction problem, where if the sort of sea level rise that we might see in the future is outside of the sample of sea level that we've seen, or the kinds of rates of forcing that we've seen in the past, or, you know, in the observations on which this model is being trained, then we can potentially miss out on certain rapid ice sheet changes in such a framework. So at the complete other end of the spectrum is, of course, mostly what we're engaged doing in the ice sheet modeling community now, and I'm certainly a part of that in other work that I'm doing, which is developing ever better deterministic ice sheet models with all kinds of fancy process representations, which give us a potentially a much better constraint on these sorts of rapid ice sheet changes that we might see in the future in this sort of out of sample prediction. But of course, all of the addition of processes make these models very expensive and only allow you to run relatively few simulations. So what's the middle ground between here? And this is sort of where we're trying to fit things in. So this project, the Stochastic Ice Sheet project, is we are going to take ISSM and we are going to replace, except for the ice flow dynamical core of the model, we are going to replace all the process representations in the model with stochastic parameterization. So the idea here is basically to build the first large-scale stochastic ice sheet model. And so the idea here is that we're trying to kind of split the difference between a model that respects most of the physics of ice sheet dynamics and can reproduce many of the instabilities in ice sheet dynamics that will lead to rapid ice sheet changes, while cheapening the model through the use of stochastic parameterizations in place of certain high fidelity process submodels. And so the idea here is that with this sort of better computational efficiency, or let's say, more bang for your buck, we can run many more ensemble members and sort of get a more robust probability distribution of the scenarios of future sea level rise. So this work is being funded by the Heising-Simons Foundation, and it's in collaboration again with the ISSM team at JPL and Andy Thompson at Caltech. Okay, so I'm not going to go back over this because I assume there might be some more questions. But the idea here that I'm put forward is that theory predicts, going back to simple applied math theory, is that uncertainty is amplified in unstable systems. And we see that that is what is occurring in projections of sea level rise, where the Antarctic ice sheet becomes unstable, and this amplifies uncertainty due to processes as fundamental as internal climate variability. This climate variability alone can produce a significant amount of uncertainty that's comparable to process uncertainty in ice sheet model projections. If we really want to be able to include this sort of uncertainty in future projections, or in the projections that we're doing in the future, starting to think more seriously about how we do large ensembles and how we use stochastic approaches to enable ensemble approaches is necessary, and we're starting to work on that. I just quickly want to also put in a plug. I just talked about the Stochastic Ice Sheet project. We have a 2-year postdoctoral fellowship, fully funded, available at Georgia Tech to work on this project. Its remote and flex arrangements are negotiable, and the 2-year postdoc is also potentially extendable past 2 years. I also want to put in the plug, if you know any great undergrads or other folks who are potentially looking for PhD programs to work on a range of problems in ice sheet dynamics, we have openings in my group at Georgia Tech. So if you are interested yourself, or you know anyone who's interested, please do not hesitate to reach out. All right, and with that, I'll take your questions. Thank you.
Thank you very much, Alex. That was a fascinating talk. Just quickly, there was a comment from Bob in the chat, just pointing out that the empirical projections that you previously mentioned were sort of originated by Vivian, who I believe is in the virtual room. Olga, I see you have your hand up. Would you like to ask a question?
Well, perhaps I would rather let others ask questions, because it could be a little bit like hijacking a conversation between two glaciologists. So yeah, if there are other questions, I'll wait.
Do we have any questions?
I'll ask one. Maybe it was buried in the talk, but what is this RCP 8.5 scenario that we heard that from the IPCC report that we heard about last week? Its biggest scenario was 150 centimeters by the end of the century. I think that's right. So I would just ask his opinion, Alex, your opinion on that. Is it good?
Is so good in the sense that, is that a good projection, or is that good for us as people?
Would it be accurate to characterize that as being the worst case RCP 8.5 scenario? Is that accurate? Not good. None of this is good. Is it accurate?
Yeah. I think the question of what the worst case scenario is it's very hotly debated right now. And I would say that is 150 centimeters by the end of the century is probably an accurate description of like what the consensus within the field is right now based on previous ice sheet modeling of like let's say a +2 sigma sort of estimate of sea level rise by the end of the century. So I think that's accurate to the state of the field. I think right now, there are a number of ongoing debates within the field about whether there are physics within our models that we are missing that particularly could push that high-end scenario up. I don't think even if you included those physics, I don't know that you could really budge the end of the century projection very much. You could certainly budge the 2200, 2300 projections. You know, I think that there's still a lot of fundamental physics that we do not understand. So, you know, to say that we won't necessarily come up with, or that there won't be studies in the future which produce worse case scenarios than that, I think would be sort of premature. That would be, let's say, like my personal assessment. But I do think that like 150 centimeters, like that's accurate for the current state of knowledge. I see Yao has a question in the chat. Does the growth of the ensemble spread for Thwaites Glacier also agree with the analytical stochastic perturbation theory that depends on the accumulation rate ice thickness at Thwaites? So yeah, that's a very good and natural question. And I would say the answer is that qualitatively speaking, yes, they agree.
Awesome.
I would hesitate to make to draw a comparison, because I think I sort of mentioned this briefly, but like comparing a 1 degree of freedom model to a, you know, 1,000,000 degree of freedom system, or, you know, a 100,000 degree of freedom ice sheet model is always, and even if they do match, I don't know that I would want to believe it, that it would have been good luck on my part.
Right. So there are a few, like you think that the two-dimensional flow might be important in determining the spread. Okay, cool.
Yeah. So something that Olga, for example, might ask me about would be, you know, that very simple model. Like it's this very like one-dimensional view. Ice flow only occurs along one plane, and of course, ice flow occurs in 3 dimensions, and in particular. You know, you can have a grounding line which is spanning a part of the bed where one part of it is reverse sloping and another part of it is forward sloping. And so the question about whether that grounding line is stable or unstable requires a sort of 2-dimensional view of how ice flow works. And that's not included in the simple model. And so that is sort of, say, one of the reasons why I would be very reluctant to try to make a prediction about the real system, or to make a numerical prediction about the real system using the simple model.
Right. But in theory, one can write down all the equations used in ISSM and apply stochastic perturbation theory to those set of equations. Is that right?
Yeah, and that's, I mean, basically the idea behind this like stochastic ice sheet project is to do that, right?
Cool.
Let's like take the stochastic stuff to ISSM by implementing stochastic noise forcing directly in the ice sheet model. And so, I mean, in that sense, that then the prediction would be, it would be an ensemble prediction, but it would be one in which, stochastic noise in both climate forcing and ice sheet processes is considered.
Right. Thank you. It's fascinating stuff.
Yeah. Olga, I think I'm ready for your questions.
Ready? Okay. So it's much more basic. As always, all devil is in the details. So as you know very well, marine ice sheet instability hypothesis is applied for the steady state, meaning all parameters are constant and do not change in time. As soon as you start changing something in time, the grounded line is moving in response to changes to those parameters, meaning it is a force drive of your grounded line. Why is it has anything to do with stability? I would probably say no, because you violate the most basic assumption that it is a steady state configuration. It's, meaning it is not even proper to say marine ice sheet instability in time-dependent sense. So in that regard, using right words is important, one thing. The other thing, Bertmann's and then Christian Schultz's proof of marine ice sheet instability has nothing to do with sub-ice shelf melting. There is no role for melting whatsoever. If you do want to include melting, then you do need to do the same analysis with melting and demonstrate that reverse slope in the presence of melting does lead to the instability. And results what you are showing with AISLENS, you literally put the feedback between the ice thickness and the removal of the ice at the grounding line. So you physically unground that point by using very specific parameterization, meaning again, you drive the retreat of the ground line by the physics that you a priori already put in your model. So in that regard, as I say, it's all devil in the details. Effectively, in both your stochastic model, which is, as Kevin pointed out, valid only for very short time periods within your steady state that you start, and in ISSM simulations, in both cases, you drive the grounded line retreat externally. So, which is perfectly fine, but then there is no place for marine ice sheet instability in these configurations. So what you are effectively showing what is a potential sensitivity of the grounding line migration weight to the external forcing that you apply towards grounded line. So in that regard, the question is, like, how do you put together big marine ice sheet instability, which applies to the steady state configuration only. And as far as I know, there is no ice sheet on Earth that is in steady state.
Yeah, yeah, these are all great points, Olga. I think if I can quickly go back to the beginning, I would say we're in perfect agreement that if I can get everyone in the field to call it the marine ice sheet flux feedback, which
is not true.
What?
It is not true, because
what?
You know very well. Because again,
I mean, there is a feedback, right? Like that's
no, and you know that very well. You know Marianne's papers. It is only true for very particular configuration. There is such a feedback.
Right. That for particular configurations, there's only a positive feedback under those cases. But like,
there is no feedback between the flux and ice thickness in the case of the laterally confined ice sheet.
Yes, I agree. Okay, so if like to move past the point about how we name it, I think this is how I would put it. In the simple model, right? The assumption of the simple model is that we can describe the ice flux as some arbitrary nonlinear function of the grounding line thickness, which I agree, like your work and Marianne's work has shown that is not always true.
And it's very rarely true, that's the point.
Okay, very rare, but like, what do you say that if we made a plot, let's say from ISSM, we made a plot of the ice flux going through the grounding line at Thwaites, like from the simulation that I showed.
How would you compute that flux? Because then you get into the dimensionality problems that Yao was mentioning. How do you compute the flux through the grounding line in 2 dimensions and show and relate it?
Yeah. Mm-hmm. No, I agree with that. I think like maybe this is a disagreement over like how applicable simple models are to complex systems. I mean, is that an accurate description? Like, I think it is. I think it is the case, and you know, I'll just posit this, that at individual places in certain marine terminating glaciers like Thwaites, we could take a high dimensional model like ISSM and calculate the flux that is going through at a point along the grounding line, the ice flux, and make a plot of that relative to the bed depth at that place. And it would draw something like a nonlinear function.
Yes, it's very nonlinear, but it depends on the other parameters, not only the bed elevation itself. And in that regard, it is not simply true to say that because it depends, it is not true to say that it depends only on the bed elevation. That's it. Because as soon as you introduce any other parameters as the width, anything else, you run into a problem that it becomes like multi-dimensional, and those, even you still look at the one dimension in one direction.
Yeah.
And in that regard, just simply going back and saying, oh, it's all marine ice sheet instability of Workman definition, which was defined for extremely specific case, that becomes problematic, because the conclusion of that very specific case of marine ice sheet instability that Workman considered is automatically applied to all other cases where all those assumptions do not hold. And that's pretty much using the words that's associated with that and applying them somewhere else automatically means that those results are valid, which is obviously not.
Yeah. Okay. So I agree, I think, with what you're saying. And I guess if I can maybe frame the results in a way that would, I think, respect what you're talking about better. In cases where the grounding line does lose stability, right?
No, it is not true. Stability applies, once again, stability applies to steady state configuration. This is the property of a steady state.
Mm-hmm.
What you are talking about is the retreat of the grounding line at some, say, increased rate or decreased rate. If the rate of the grounding line migration is 0, it is stable. The reverse is true. In the steady state, the rate of the grounding line migration is 0. But the opposite, that if the grounding line migration rate is 0, does not imply that in steady state. It implies that for a given period of time where you're looking at it, it does not move. Say 5 years later, you look at it and it starts moving, but it doesn't mean that it wasn't steady state.
So if I perturb to the system, a system.
Which system? Are you talking about the steady state?
I'm talking about if I had Thwaites in a steady state in reality, right? So that is to say,
Not the Antarctic ice sheet has never been in steady state. It could potentially could be an equilibrium, but it's not a steady state. That's
if it was in a state and I perturbed Thwaites by changing the climate forcing.
Yeah, it would start evolving.
Right. So such that the evolution took it to a different state.
Well, it will be moving through different, at every particular moment, it will be moving through different states.
Mm-hmm.
And the history of that move does affect all the next states. So the integral history does affect that.
Right, yes. But if it were the case that I perturbed it in a way that took it to a different state that was sufficiently different from the initial state, and that the magnitude of that change did not depend on the exact magnitude of the forcing.
Yeah. No.
Would we agree would we agree that that change would represent something like a bifurcation in the dynamics?
Not at all. Not at all. It would not represent that, because again, it is a time evolving problem. I completely agree with your point you're trying to make, that the response is highly nonlinear, and say if the climate forcing it does not change and you observe the retreat of the grounding line, that it's very tempting to say then it is unstable and does it on its own because there is no immediate obvious change. But the whole previous history and the highly non-linear response to external changes in the external forcings, they can lead to very rapid movements of the grounding line. And it can move in both directions. However, as you started your talk, it's extremely simple thing. It's the grounding line advances if the accumulation rate or accumulation, the integrated accumulation exceeds the flux through the grounding line, and it retreats in the opposite if the flux through the grounding line is less than the net accumulation rate that goes into the ice sheet. That's it. As soon as you perturb this balance, the grounding line moves, and the direction is determined by only those two things. So, but at the given point, what is the flux through the grounding line? It is certainly not Christian's expression.
Yes. Okay. I agree with you on that. I think as we've talked about before, like I think we're largely in agreement about the issues here, and just generally the issues and about how we talk about these things in the field. And so I know that I'm like using the wrong language that people use about these things. But that's just largely because the kind of thing that we're talking about, the kind of response of the system, even if it is incorrect to call it an instability, it is strictly speaking incorrect to call it an instability. It describes something that happens when you perturb this kind of system. Not instability. I'm saying it's just a label that we use to describe a certain magnitude of a response. And I'm not saying that that's correct. I'm just saying that's why I use the term so that other people know what I'm talking about.
I understand why you're doing like the rationale, but it completely shifts and makes the results not your results incorrect. The consequences of interpreting, it's, as I say, all like devil in the details and what you're saying. So effectively, it is the response, highly nonlinear response to changes in the climate system.
Mm-hmm.
Nothing more, nothing else, and it is highly undesirable to talk about stability and instability because these are properties of completely different systems that those systems have never occurred on Earth, Laurentide ice sheet does not exist, meaning cannot be in a steady state. The similar is true for Greenland ice sheet that evolving with time, and the similar is true with Antarctic ice sheet that still responds to last glacial maximum. So the interpretations do matter, and words do matter. Using them appropriately makes things much clearer, in my view.
Yeah, I guess the question that then I would have is, if we agree that the system is not in a steady state, and so that makes it, let's say, inappropriate to talk about these things and to use these sorts of approaches, I guess my question would be, is there a way that we can understand how the uncertainty evolves in a projection, right?
Yes, of course, and it is somewhat along those lines that you were showing, like then you just start considering a time evolving solution and you perturb all those parameters and you write those things, but you start not from a steady state, but from a time evolving system. There is nothing wrong, but it is highly inappropriate to replace one with the other. That's the only thing. So yes, it is possible to understand. Yes, it's all well taken, like stochastic simulators and trying to estimate uncertainties and staring at those equations that go into the model. That helps quite a bit. But applying the machinery, which was developed for systems that are highly unlikely and have never occurred in the field that we're trying to study, it makes results by default inapplicable.
I mean, so what I would argue is that even if we sort of removed the, let's say, the requirement, or not the requirement, but if we removed the assumption that the system was initially at a steady state, and
you start from any initial condition, but just forget about steady state. That's it.
Okay.
And you start moving your grounding line in one direction or the other, and just moving, it's migrating. Yeah. If at some point its migration rate is 0, that's great, but next point it's non-zero. So the fact that the grounding line migration rate is 0 for that particular configuration at this particular moment is no different from any other configuration where the grounding line migration is not 0. That's it.
But the result, I mean, like, so qualitatively speaking, the result that, you know, we would expect the uncertainty to grow more quickly during the periods of, but during the periods of the simulation in which it is evolving the most quickly due to the nonlinearity inherent in the dynamics of the system, just calling it that. Like, do you?
No, I do not think the magnitude of uncertainties and rates of the grounding line migration have something correlated. Let's put it this way. I do not think they're correlated at all. No.
But then, so like, is it just a coincidence that in pretty much any ensemble simulation that people have run, that the growth rate of the uncertainty is generally at a maximum, or almost always at a maximum, during the time periods when the growth rate of the ensemble mean is also at a maximum, or the sort of change in the ensemble mean is also at a maximum?
Yes, and I would think there is some physics. Yeah, it is possible to write something physical, but I do not think the two rates in the amplitude are connected.
Okay. Yeah.
So that's.
Can I interject?
Yeah, of course, please do. I was waiting, Craig, that you just say, please shut up. Yeah, that's why I suggested. Yeah.
I'm really sorry I cut you off.
That's fine.
I misheard you. That was terrible of me. We have a couple more questions in the chat, and then we should probably sign off because we're well over. But this chat has been fascinating. So we have a question from Gavin. Does ISSM exhibit an effective marine ice sheet instability in full simulations for Thwaites, i.e. accelerated loss? The question is sort of how good is ISSM at representing ice sheet instability for Thwaites?
I think ISSM is about as good as any ice sheet model. Given
no, that wasn't the question at all. No.
Oh.
The question really relates to what you and Olga were arguing about, right? So my desire to get into that particular hornet's nest is small. But if in full simulations you see things that look like an extremely accelerated loss that goes beyond any change in the forcings in the Thwaites Glacier with the full three-dimensional calculations, right? That's my question. Does that happen in these models?
Yeah, well, I mean, so as you saw from the simulation ensemble, like in ISSM, if you force Thwaites with constant ocean forcing, it will go through a period of accelerated loss. It has an S-shaped response curve, such that you go from some initial state, which is not at a steady state, to a faraway state that is qualitatively different from the initial condition. So in that sense, like, yes, the answer is yes. You know, the extent to which we call that a marine ice sheet instability, I think, is part of what Olga and I are sort of discussing. And, you know, whether it is appropriate to call it an instability. I think Olga is correct in saying that there is a lot that evolves about the system such that it is inaccurate. Like during that period of accelerated ice loss, there is a lot about the system that changes such that it is hard to call it an instability because there was no initial steady state that was being lost through the instability.
Yeah, no, see, I don't like that as an argument. Like, so the statements about stability or instability and equilibrium points are statements about the underlying manifold, right? They're not statements about where you are in any particular time period, right? So in time, they're not going from a steady state to a non-steady. I mean, like in time, you're moving around all over the place because there's a lot of stuff going on. The issue is whether whether the shape of the underlying manifold is changing such that something that was not a limit cycle, but a kind of basin of attraction has disappeared, right? Which is a totally valid statement to make even about a time varying, complicated system. It's not, you know, we're not, yeah, I mean, anyway.
So if I think I know maybe what Olga is going to say in response to that, but I'm not going to put words in her mouth. But I think that the point is that there is a set of assumptions about marine ice sheet dynamics such that the thing that you're describing is true, right? That there is a basin of attraction that goes through a bifurcation that then takes you to a different basin of attraction, right?
See, that's okay. So I disagree with that statement because it's not the changing of the basin of attraction that takes you anywhere, right? The basin of attraction is the manifold shape upon which your time varying state is moving around, right? The change of the shape of the manifold doesn't move you anywhere. It just makes the your specific time evolution trend towards something else later on, because now it's not being dragged to this basin of attraction over there, it's being dragged to another one over there, right? But the basin of attraction doesn't move anything, right? They're the landscape upon which your random thing is moving around.
Darren, I'm not sure it is an appropriate picture or framework, if you wish, for this particular application. And again, there is a danger in it, somewhat similar. I'm not saying it's exactly the same, but somewhat similar with the marine ice sheet instability. So that's, I'm not sure if my intuition is not great over here to tell you why there is such a manifold and the basin of attraction for an ice sheet. And the simple reason, because ice sheet cannot exist in isolation, and they are part of a climate system. And so there are such things as feedback. So that's why I'm kind of trying to put it to get to the answer to your initial question about the ISSM and what's happening over there. So although Alex said that climate forcing was the same, the parameterization for melt rate at the grounding line is a very positive feedback, meaning the thicker the ice, the much higher melt rate. So meaning by using this parameterization, there was a mechanism embedded in the simulations a priori to drive the migration of the grounding line, because you physically remove mass and make it thinner. So in that regard, yes, the climate forcing is the same, but or in ISSM has a very positive feedback that drives the retreat.
So yes, what you say is correct, Olga. I think it would still be the case that all the results that I showed would look approximately the same, even if we did it without the feedback that you described, right? So let's say we just turned out. No, I'm saying that is the case. I'm saying
so okay.
And you can look in the supplemental material of the paper. You can just turn down snowfall, and you will get the same thing. I think I want to get back to Gavin's point. So I think the point here is that in the very simple versions of the system dynamics, right? Like the one-dimensional version that I showed, or close to one-dimensional versions of the system, like there is a bifurcation in the manifold in the way that you described, Gavin, in the sense that the manifold exists and you can move through the manifold such that you go through a bifurcation. As you move from that very simple, all the assumptions that go into that very simple description, the manifold that you see in real ice sheet systems and even in just complicated ice sheet models becomes more complicated in a way that, and this is what Olga is saying, like, which is very true. And, Olga has done some great work on this, that like you can get into a situation basically where you can have, for example, stable grounding lines on reverse sloping beds because of the change in system state that occurred as it evolved past let's say like the bedrock peak initially. Right, and so basically like—
they are mixing things, the stable applies to a steady state, and how you get to that steady state, you have no clue. You have just a kind of a snapshot. It's a timestamp, like time snap. You took a picture. It is in steady state, but how you got there is no information. And actually, how you get to those steady states, or what you call stable positions, it does matter. And that's what is determined, and that's why the manifold becomes significantly much more complicated than just putting here is a stable position, here is a stable control, or the steady state position with a stable grounding line, and steady state position with the unstable grounding line. Because honestly, to get to an unstable position of the grounding line in a steady state in time evolving case, it's impossible because it is unstable. So
I don't know if Gavin wants to.
I was shy. But yeah, thank you guys for letting us. Having a great chat. So.
I should say this is a great discussion, but
Can I ask one final question? Sorry, this is Allegra. Sorry. Can I ask one final question before we sign off? Have you tried to look at the last interglacial? How do you find the West Antarctic in the last interglacial? What steady state do you?
So I have not tried to look at the last interglacial. I know that others who have generally found that.
I meant specifically with your setup, like the setup that you have, like the boundary conditions, the way, are you able to kind of get in a ballpark where there's something like at least 3 meters and maybe all of West Antarctica gone during the last interglacial?
Well, this sort of gets back to, I think earlier question about, whether we think like 150 centimeters is like a decent projection for the end of the century. Actually, a lot of the debate, right, over whether we are missing model physics that some people want to put into our ice sheet models is largely around how sensitive West Antarctica is, and actually parts of East Antarctica as well, are to small changes in local temperature relative to our modern day temperature, right? And so I think the answer is that depending on what you put in your model, you can get those 3 meters or you cannot get those 3 meters. And this is precisely like what is at, what is under discussion here is like whether those extra physics are realistic, are supported by observations, and whether they are strictly speaking necessary in order to reproduce paleo sea levels.
So if you had to rank extra physics in a more specific way, what would be your top 5 or 2?
Oh, so that's the thing, is that, I mean, like the main debate that is going on in our field right now, well, it is not the main debate, but specifically with regard to this question, the main debate has to do with the fact that we do not really understand what controls iceberg calving to a certain degree. And particularly in situations where you might have a very tall ice cliff that is sitting in the ocean. The hypothesis that has been put forward is that cliffs like that are structurally unstable and so will lead to very large retreat rates, similar to what we currently see at Jakobshavn Isbrae in Greenland. So I'll just say that is what people have put forward. And then they've simulated the last interglacial, and they have found that,
like Doug McGale's saying, like with dominoes falling, like from 15 years ago.
I don't want to like turn this into a sort of discussion about, but there's a paper by Rob DeConto and Dave Pollard that was in Nature in 2016, where they had sort of put forward, or they had used this idea that actually Jeremy Vassos had originally put forward in a 2012 paper, that these tall cliffs are unstable. So the point is that in West Antarctica, if you expose these really large cliffs, because West Antarctica is very deep below sea level, then you can get these, potentially, you can get these very tall cliffs. And their hypothesis was that these large cliffs would produce retreat rates of order like many kilometers per year. And this would get you, like under last interglacial conditions, that would get you to the like few extra meters of sea level. So it's sort of like, it is a let's say like what's the right way to put this? Like, they put forward a hypothesis and they showed that under the assumptions in this hypothesis, like you could get to the few meters. Whether the hypothesis is true or not is sort of like what's under debate. And so now, since then, there have been multiple papers kind of on both sides of the coin saying, one, there was a paper by Tamsin Edwards in Nature last year saying that you actually don't need this extra physics in order to get those multiple meters worth of sea level during the last interglacial. There have been more recent papers, some of which I've been involved in, having more to do with the specific physics of the problem of how do you quickly remove ice shelves from around Antarctica, and then what is the consequence of that on the rate of calving at the terminus of glaciers. But that is very, like, it's a very active area of research there. So I definitely wouldn't say one way or the other whether we've resolved that debate. But I enjoy watching Olga give her facial expression because I know she has strong opinions about it while I try to describe the most impartial.
Yeah, let's just describe all this highly speculative with very little physics underneath. So
yeah.
Thanks.
Thanks.
We should probably end this.
Yeah.
lively discussion.
Olga and I can take it to the next conference because we usually end up talking about it at conferences anyway.
Thank you so much, Craig, to allow us to have another face-to-face conversation.
Well, thank you all so much for a great discussion and all the great questions, and thanks to Olga again for all of her great questions and points as usual.
Yeah, thank you again, Alex, for a fantastic talk, and thank you for everyone for joining.